Hello everyone, and today we're back again on CodeForces. This is Division 4 round, which means that the tasks should be quite simple. I'm competing not rated on this round. We will be using the CPH Judge extension. For those who don't know, check out my other videos on the channel. We do these live competitions all the time, so yeah. The CPH Judge extension allows us to just simply parse the problems. There are three cards with letters. So problem A, there are three cards with letters A, B, C placed in a row in some order. You can do the following operation most one. Pick two cards and swap them. Is it possible row becomes A, B, C? So there are only six different permutations. So it is only impossible if there are these two permutations. So if S is equal to this, or S is equal to this, okay, we will go immediately up to problem B. Problem A gets accepted. Okay, so this is quite slow, but okay. Slavik is preparing for a present for a friend's birthday. He has an array of A of n digits. The present will be the product of all of the digits because Slavik is a good kid who wants to make the product biggest product possible. He wants to add 1 to exactly one of his digits. What's the maximum? Adding 1 out of his digits. So we can try to the number of digits are very small, but so yeah, so we can just brute force that. But okay, so yeah, let's brute force that. Okay, that's good. That should be good. Okay, so there are 10 by 10 target made of 5 rings. Each ring is different. Okay, Vlad fired several arrows at the target, helped him determine how many points he got. So he has these things. Now, what has each ring described? Each ring is described by the distance from by the minimum distance from some edge. So there are some strings. There are exactly 10 of these strings. And then we will just iterate over each and then points. The answer will set 0 if I j is equal to this, then answer is plus equal to the minimum of ij 10 9 minus I 9 minus j, and then plus 1. I think that should be fine. Okay, let's go D. 1D eraser. You're given a strip of paper S that is n cells long. Each cell is either black or white in an operation. You can take any k consecutive cells and make them all white. But find the minimum number of operations needed to remove all black cells. It's either black or white. Then to remove all black cells, we just, for the first black cell, we have already like how many. So this is a really cool educational problem actually. There are this really cool educational problem. I have seen it multiple times. So if S of I is black cell, oops, on the eraser. Okay, so operations. If this is black cell, if max is smaller than if max is bigger than equal to I, then just continue, else we need to operations plus plus, max is I plus k minus 1 or something like that. So I think that's correct. So if this is the case, then this max is maximum of max and I plus k 1 operation plus plus. That should work. Okay, problem E, building an aquarium. You love fish, that's why you said to build an aquarium. You have a piece of n columns, AI units like, pick an integer h, build walls of height h on either side of the tank. Okay, then fill up the tank with water so that the height of each column is h, unless the coral use water. You can use most x units of water to fill up the tank, but you want to build the biggest tank possible. What's the largest value of h you can select? If you want to build the biggest tank as possible, but you have this many units. Okay, so you just binary search. Okay, so what are the n and h, n and x? You just want to binary search h. And x. So the water here is the minimum is the water is calculated that the H, if H is it's the minimum, so water plus equal the A of so H minus the mid minus minimum of mid and this, right? If the water level is bigger than X, which means we can't do it, R is mid, L is mid. I think that should work. That should work. Okay. Lucas is in front, so problem F. Lucas is in front of N-trees. The I-trees has AI fruit and HI height. So can I see just the standings maybe and see? Oh, 36 in the world. Nice. I fruit and H height. He wants to choose a continuous subarray such that for each integer hi is divisible by hi plus 1. He will collect all fruits from each of the trees in that subarray. However, if he collects more than k fruits in total, he will get caught. What's the maximum length of the subarray he can choose if he doesn't get caught? Okay, so what is the most length that he can choose? So the arrays are really big. Okay, so is it binary searchable for each L point? We can binary search whether. Okay, so because hi has to be divisible, this has to be a monotonic function. Okay, so this is a monotonic. Hi is divisible by hi plus 1, so this is a monotonic function. He will collect some fruits, which is, again, we don't care, but we want to make them as bigger as, this array as bigger as possible. So we just binary search for each starting point. So, okay, let's call that. Yeah, so NA vector A H so this is going to be from each starting point. We're gonna somehow binary search R, but we need to answer really quickly, is that fine? So the answer here, the maximum length. How to check hi is divisible by this? Okay, so we can collect, we can make prefix sums for. Okay, so this is the prefix sums binary search, if that's all right. Is it? Are they all possible? Yeah, all possible. So let's okay. So L is L is possible. Then R is N, which is impossible. 1 minus L is bigger than 1. Okay, so want to say that is the prefix sums, are the prefix sums, so the sum here is prefix at this is prefix at mid minus prefix at L. Okay, so this L minus 1 prefix L minus 1. So if sum is bigger or equal to but the divisibility is a monotonic thing. The divisibility actually, I don't need to binary search. The divisibility is actually just a logarithmic time. No, I don't need to binary search. I can just brute force. For each L has to be divisible. I don't even need the prefix sums, but whatever. If h of r divided by h of it is divisible by this. If it's not divisible, I'm going to break it. I will say the answer I don't need prefix sums. Sum is just a of I, a of L. If sum is small, at most k, more than k, at most k footage. Okay, and then there's this sum equal plus equal a of r. Then of course I need this sum equals plus a of r. Then we want to then this if this is the if this is not divisible, then we break. Else we say that answer is the maximum of answer and r minus l plus 1. If sum this oh, we have wrong answer on test 3. Building an aquarium, wrong answer on pick an integer. Wait, what? It can't be 0, maybe? right? I'm searching for what? Pick an integer height. The height if water is bigger than x. If water is bigger, x units of water to fill up the tank. If it's bigger than x, then we can't do it. If it's smaller or equal than x, then we can do it, and we can increase the height. What if x is like 1? So let me just make a case here. If x is 1, and we have water is the mid-level. Okay, that's correct. That's correct. Mid level minus, so the height minus. Will time limit exceed? Wait. Isn't it logarithmic time, the divisibility? It is a logarithmic time, it has to be. Oh, but what if they're all ones, right? If they are all ones, they are all divisible by that, right? Yeah. So okay. So if they're both ones, then we want to say how. Then we want to binary search actually, right? But why don't we just binary search all of them by the? Break if h of r minus 1 is 1 and h of r is 1, then binary search, let's say. So int r is my r, and then So my R is already inside, and then so this is my left, my R is in. Okay, so okay, now I need prefix sums. I don't know why I deleted it, but there. So binary search. But you don't know if they're all divisible, right? Yeah, you don't know. So yeah, we're going to delete all of this. We're gonna say the following. We're gonna search from L to N, but we're gonna have two prefixes. One prefix will be for A and the other prefix will be for H. Prefix H is going to be or do we need to combine them? We can solve this problem in many ways, but what is the easiest? Combine them doesn't seem... So all of them do divide until it comes to like 1. And then up to... For each of this, I will say what is my last point which is valid. So last valid at n-1 is itself n-1, right? So if hi is divisible by if hi is divisible by hi plus 1, then last valid of I is last valid of I plus 1. Else last valid of I is I itself. Alright, then we just binary search. We say, okay, we have some middle number. Okay, this is okay, so the sum is prefix at L minus prefix at mid minus 1 is big, L minus 1 is bigger than 0, then prefix at L minus 1, otherwise 0. Then there's last valid is last valid. Actually, we want to only search up to the last valid. So here, last valid of L plus 1, right? And okay, so this is the sum. If sum is smaller or equal than k, then L is mid, otherwise R is mid, cancels, max cancel, L minus L plus 1. Also, yeah. So if L is not L, then this. Else, if A at L is smaller or equal than K, that should work. That should work. Last valid prefix, L prefix, and I think that should. No, what is this? This is F, right? Matrix. This, I don't know what is going on with this. I will just go G and H solve. You're given a string S made of characters A, B. You initially have no coins. You can perform two operations. Pick a substring A, B, change it to B, C, and get a coin. Pick a substring B, A, and change it to C, B, and get a coin. Okay. What is the most number of coins you can obtain? Alright, so this is kind of a DP problem, right? So F gets accepted. Also E, we have to fix it. But let's say this is DP. So if I change the B, if I change this B, so this is like DP of N. If S S substring I minus 1, 2 is equal AB, else if S substring I minus 1, 2 is equal BA. So if it's equal BAB, then I can then I will do this. So I will add a auxiliary character just for the sake of it, and then I will start at 2, and then I will say dp of I is the max of dp of I, and dp of I and dp of I minus 2 plus 1, dp of I and dp of I minus 2 plus 1, and then we want to am I missing something? I'm missing something. dp of, yeah, this minus 2 doesn't work. If b substring ab and change it to bc. Oh, of course, but changing it to bc, then there's it creates this so if there's like a b, then like you change it to bc, and then you do this a here, b you change it again to bc. So if there's like a b, you change all of these a lot to bbc, to bcc, like this, and then if there ba, so if there are a and b, what about if there's more b's? There's ba, you change this to cb, but then there's like, what if there's here an a and then you change this? So what if there's here a b, So for each B, you can go and change how many A's are on the left and on the right. You either change the A's on the left or you change the A's on the right. Is that correct? I think it is. Each B, for each B you change. So here two, yeah. Okay, so if there's B, then you have to pick the DP from here, like on the left, or so you just don't change. Essentially, you don't change the you change all of the A's inside. Some B will change these A's, some B's will change the other A's. Only A's at the end won't be changed. If there's at least one B, if all of them are A's, then there's 0 changes made. Okay, so now consider there's one B, then all of the A's until that B what if they're all B's? So if there are all B's, if they're all B's or all A's, and we don't change anything, then there's some A and some B, so we go if A of I is equal to B break, so this is minimum 1. This is count 1 and count 2. Count 1 plus plus. Now we say, okay, this is S of I. Now we go the other way around. And we say, when it's B, we just break, and then this is C2 count, and then the answer is all A's. Count A's minus the minimum of C1 and C2. Count A's is just simple. No, but here you see that's not correct because we just pick. Well, if I have this, then that's okay. Then this is the only case where this is wrong, right? So if I have 2 consecutive P's, then I can actually manage them all. So I need to check that in consecutive. If the substring is BB, then consecutive is 1. Then if consecutive, let's see out. We can do all the A's, else it's just this. I think this is the problem, and then Mad City. Okay, let's fix problem E. Oh, okay, that's not a problem. Oh, okay, let's. Well, if they're all B's or all A's, then it's 0 definitely, but I don't see how. One A is removed in both operations, so the number of A's is just invariant. I mean, the number of A's is just tensor relies on this. Okay, so that's return. If I find a B, I will break here. Then the count of all A's is what else I find. If there's two consecutive B's, which means that one B will, if there are two consecutive B's anywhere in the string, this B will change all of these A's into like CB, and then so if there's like AB, this will change it to BC, BC, BC like this, and this will change it like this. Yeah, let's imagine this case. Right, I say that there's 3 because this will change BC, this BA will change CB, and then this C is actually dividing this A to come to here, so this just changes like this. But I can choose actually to do BC here, and then go into this direction. So if there's, oh, there cannot be consecutive. If they're like this consecutive, then I cannot choose to change anything here, since but if there's this consecutive, then the minimum here is 0, which means every of these will change them. Or if it's like the other way around, it's again 0. Oh, but maybe I can do, yeah, so maybe I'm actually just wrong, and I say that if there's some case like this, I can choose that these are changed and some other here is not changed. So it's not actually the minimum of these, but like minimum block. And then this minimum block is going to be like minimum block is if s of I is a, then count plus plus. Else, if it's b, then minimum block is the minimum of this and the count, and count is reset back again. So the minimum block here is this, and then if the count is, so we count the first ace, then b, then the second ace, but then there's some like ace here in the end, which is counted as well. So if minimum block is bigger than actually it's fine. I think that should work. Okay, now problem, is it problem H? I mean, yeah, okay. Problem E, what did we do wrong here? Problem E, what did we do wrong? We just binary search and we add the difference. Pick an integer and build a wall. Largest value of H you can select. Oh, you can select much more than that. You can select a lot more than that, actually. This is the mistake here. I think this is the mistake. L plus R minus L divided by 2. It's not just overflow that. Okay, so that's the mistake on E. Select a lot higher H than. Right. Can you select even higher than that? No, you possibly can't select higher than that, right? 10 to the 9 times. Yeah, it's overflowing here water is overflowing. Then this here AI times 10 to the if water is bigger than X, break. Okay, a nice problem. I like that it's not that straightforward, just binary search. Start at buildings, so are in Med City and buildings and two-way roads between them. Start at A, B respectively to catch Valerie. In other words, be in the same building, him or meet on the same road. During each move, they choose to go to an adjacent building of the current one or stay in the same building because Valerie knows Marcel. So, well, can predict where Marcel will go to the next move. Can use this information to make a move. They started and ended at the same time. It is guaranteed that any pair of buildings is connected by some path, and there's some road between. Okay, a simple answer. It has a strategy to indefinitely escape Marcel. So I can use this information to make a move. So he can predict where Marcel will go to the next move, and now it's the thing is can Valery use this information to escape indefinitely? Okay, let me just take a look at the standings. Okay. Can he escape? Can he indefinitely escape? So depends on the positions, right? Depends on, because there are two-way roads. It's a tree, but with one cycle. So it's like, okay, so you have some, I mean, whatever, you have like one cycle, right? And then if they're both on the cycle, Marcel can predict, Valery can predict where Marcel will go, then thus making can use this information to make a move, and now it can indefinitely escape, right? If they're on the cycle. If they're not on the cycle, if Valery is on some like branch outside of the cycle, now depends on which position the Marcel is. So okay, so pretty straightforward problem. I like the problem. Let me just see how I read the input. NAB. There's some vector adjacent Now the trick is to find the cycle. To find the cycle, these are all helpful things, helpful arrays to find the cycle. Maybe this is not needed, but I'll just call it for fun. So just start anywhere, doesn't really matter. For every adjacent if B is parent, continue. So here we just say that okay, so visited at P strum in stack not P U in stack this is strum. also we kind of need some stack, so this is some stack st. If in stack v, so if it's in the stack, or else so if it's in the stack, then there is a cycle, and it means while stack is not empty, and stack dot back, because I'm using let's just use this normal stack dot top is not v, it's not u actually, or whatever, it doesn't matter. I mean, I'm pointing to some node, is not v here, then in cycle at s.top is true s.pop. So that's a cycle. We put all of these nodes to a cycle, right? And then okay, so we put all of these nodes to a cycle. Else, if it's not pasted at v, then dfs v u. Okay, now we need another visited. I will use the same visited array. I can just do this. Okay, so you use another array, and I mean the same visit array if it is a cycle and it's not. I mean, I don't even. So for each of these cycle, I'm going to push another DFS, and this time the same thing, but this time if in cycle v, then I'm going to continue. I won't push there. So if so who has to be in the cycle? If the cycle is there, if both of them are in the cycle. So first we just say like this: if in cycle a, if both of them are in cycle, then it can definitely, if Valery is inside the cycle, it again can definitely. So if Valery is inside, is Valery A? The number of buildings of Marcel and Valery. So it's B. So if Larry is inside the cycle, Marcel can't do anything. If Marcel, so if Larry is inside, so if Larry is not inside the cycle, Marcel doesn't kind of matter where it is, as long as it is on this. So okay. So if it is in the cycle, I'm going to push another DFS, and if that DFS comes true, then yeah, then no. Let's say that this cannot be escaped. Otherwise, yes. And then now here we're just going to push state. That state is 0. If now Valeri here they have to be outside. I mean, there's probably a better solution for this, but whatever. Boolean. So if DFS to VU, and now the state is the following. The state if U is equal to A, so to Marcel, the state changes and state is 0, the state changes to 1. If U is equal to A and state, if U is equal to B and state is 0, then return false. If U is equal to B and state is 1, return true. Okay, if that's true, return true. Return false. So we just go to the next if it's not in a cycle. Yeah, if it's not in the cycle, so it's like outside the cycle, we check all of the branches. If this is the case, we set the state here to be 1. If this is in state is 0, return false. This state yeah, so okay, so this okay. Wait, we have more test cases. We don't read something well. NAB. Then we read 3. Oh, we don't return something. Okay. So this correct. The first one isn't correct. The first one is just the cycle, as far as I understand. All of them are in a cycle. Should quite clearly return yes. It doesn't find the cycle. True in stack on this in stack V is a cycle. Else if it's not visited. DFSV and then U. Wait, after this I just want to of course stack is not pushed. Stack.push U stack.pop. So let's see, here when it is no, when it is no here, so there is some cycle, and there's 5 and 3. Is 5 and 3 in the cycle? Five is inside the cycle. 5 is inside. I think this passes the case where this is the, yeah, so this passes here, but then something goes wrong here. So if A, wait, are they reversed? First is B and then A. Wait, if the state is 0, so we haven't found something, then and then this is Marcel, which is A, and the state is 1. If the state is so Marcel is on 5, which is this, then the state here is 5, 0, 1, 2, 3, 4, 5. The 3 here is not in a cycle, which means that wait, but what if wait, the distances here is very, if this can come to a cycle node before this comes to that node. So we don't need this DFS, but we need the distances between these two nodes. So we will push a DFS from, let's write another DFS. And let's write it like the following. So this is like the distance. If in cycle V, then we return 1. This is the distance. If we return 1, and then we return D is maximum of D and DFS3 V and U, because this would be 0 and there would be some like distance. to this point. So we want to maximize this distance from the point of here, and then okay. So what we do is we send it from Valeri's point of view, which is B, and we get distance to cycle is this. And now we also want the node to actually, like, we want on what node do you end up in. So this could be done like just simply like this. Node is V. And now we want the distance from the shortest distance from A to node. Right, so we need some U and V. From set U is 0. Distance at U at V actually. So this is the distance. The shortest distance, shortest is BFS A node. And then if shortest distance is smaller than distance to cycle, smaller or equal to distance to cycle, then it's yes. Then it's no. I think that's the case. Here we say yes, because B is inside the cycle, which is incorrect. Probably. Okay, so that's this case. 1, 1, but B is inside the cycle. 1, 2, 2, 4. Yeah, so this is a cycle. 1, 2, 4. B is inside the cycle, and A is inside the cycle. Oh, if A is equal to B, then of course it's no. But that's an edge case. Otherwise should be. So the idea is how close is it to the cycle? The distance this to cycle and shortest is 2, and then the distance is 1. Are you sure that the shortest is 2? Apparently yes. The shortest is 2, shortest to the cycle, to this node. But B distance to the cycle is 1. Okay, so let's see where B is. B is 3. The cycle is quite complex, but I would say that this is definitely incorrect because you need +1 something here. This is distance +1. Right. The distance to the cycle, this is +1. The distance is, this is DFS of 0. Image map. I'll just submit to see because we fixed all of the other problems. Okay, wrong answer. Why is wrong answer? Distance to the cycle. All we can do instead of just this DFS, we can do it in BFS mode. We just say that the distances are all this, and then here we'll turn a pair. Okay, that's correct, and we'll iterate through all of these and say if in cycle I and int best this is like int max, int best node is -1, if dist of I is smaller than best dist, and here I can do dist to cycle and node. And this is my second BFS, which starts from 0. That should also work. That I'm not sure if that's correct. Distance is 2 and the node is 5. 5 is 3, 8, 8. 6. Huh. Are they not all in the cycle? 1, 2, 3, 4, 5, 6, 7, 5, 6. Wait. 3 to the 3 to 8, we go 8 to 6 or 8 to 4. 6 to 2, 2 to 1, 8 to 5. So in the cycle there are 5, 6, 7, 1 and 2. 1, 1, 5, 5, 7, 7, 6, 6, 8. So 6 should be in 6 should be the first node. Yeah, that's why it's 5 here, because 0 index. So 6 is the first node, and we want the shortest distance from 6 in point of view to 3 to 5, right? So 5, 7, 7, 6, so there's 2. So the shortest distance is 2, and this is 2. If the shortest distance to that node is smaller or equal to the distance to the cycle, that should be correct. No, this has to be right. I don't see how this cannot be right. This maybe just distance to the cycle is incorrect in some case. Should we submit once more time? No, I don't think. Huh. Okay, this was incorrect. The DFS was incorrect for some reason. Okay, so we solved all the problems. But with a couple of wrong answers, so it wasn't the best performance, especially for stupid wrong answers such as like limits, and I have to be careful with limits more, and things like that. So like just writing this DFS out and without noticing that actually the distances matter. Things like that can become. So yeah, this gets accepted. Let me just see the standings, and I will upload the video right now. I mean, yeah, fine. I don't know. The performance is somewhere here, but should be quite faster and without these penalties for the wrong answers. Should be quite faster. I don't understand why. Just in 7 minutes, this was kind of cool performance here. But okay, so yeah, thank you guys so much for watching, and I hope. Okay, yeah, wait. Should I explain all the problems? I think that were easy, but okay, let's go. We have time, just 1 hour. Okay, so okay, let's go over all the problems. This first problem, you see that the test case only go to 6, and there are only 6 permutations in which ABC can be put in. So for for 2 of the 6 permutations, because of the parity, I think, of the permutation, it's impossible. Not the parity, but it is yeah, should be the right. But it is impossible if you swap only like 2 cards here. Let's say this. It is impossible to make that permutation sorted by just one operation. So essentially, you're asking just one swap, and this is not just the parity. This is just like, I don't know how it's called, but with one swap you can't do it. We need 2 swaps for these permutations, and we can just hard code them. We don't need to count how they are distributed and such things. Okay, so this is problem A. Problem B, you have a array of A of some n digits, and you want to add 1 to some of the digits and to make the product as bigger as possible. So there are many ways to solve this problem. One can solve this in linear time if he wants to. You can essentially make some prefix. No, it doesn't need to be prefix. You can just make the whole product and then divide by this number here, divide by the number you want to change, and then multiply the number you are changing it. So just you can solve it in linear time, although it's just easiest to code in quadratic time as well. So quite an, I mean, easy problem. This C, you just want to, you have these points for each of the rings, and you are given this array where the targets are hit. Now you're asked for the amount of points he got, the sum of all of these points he got. And the thing is that all of these rings can be described with some invariant, and I mean for this ring, the minimum from the edge, from the minimum, so for any point you can have some distance to the edge, to some edges. The minimum distance to one of these 4 edges describes the value of the ring. So here the minimum distance any point of this is 0 to this edge, and thus the value is 1. Here it's the minimum distance is 1 to some edge, and then the value is 2. So what you want to do is just iterate over the whole matrix, and then if there is x, you want to sum up the minimum, whether it is I, j, 9 minus I, 9 minus j, so it's 10 minus 1 times minus I. So minimum of all of these, and plus 1, because we know that the minimum will be always like 0 here, but we want 1. So remap them somehow, and then the answer is just the sum of all of these. I mean, okay, really quite easy problem. D here, 1D eraser, so you're given some string and you want to remove the blacks, remove all black cells in the string, and you can make this operation while you take k consecutive cells and make them all white. So like some operation where you paint k consecutive cells, and it's quite easy to see that greedy solution will always work. And since we pick first, we pick this here and we paint the next k consecutive cells, and then here where this black, we want to paint the next k consecutive cells, but it doesn't really matter if there are no cells. I can just shift and paint them like prior to this, right? Since k goes up to n, there won't be any problem. And the solution is just when I see b, either the maximum that I'm painting right now is bigger than 9, which this b actually kind of is already inside, or if it's not already painted, already inside this thing, we want to make the operations +1, so we want to start painting from there, and we're going to end up painting at I plus k minus 1. This is going to be the next stop where this is going to be painted. So quite an easy problem. Problem E, yeah, I didn't see the limit on problem E, but we knew that this problem is just a binary search problem, and we can, because we're asked for the largest value of h that we can select, the more h we select, the higher h we select, monotonically increases the water in the tank. So if it's monotonic increase, it means that we can binary search for what h is the highest, such that x is the lowest, x is at most, the water level is at most x units, right? So that's what I want to say. And here the water is going to be added up the midpoint where we select this h to be, minus the minimum of the mid, and this is just mathematics. This is just to avoid if statements. And then if the water becomes greater than x, we can just break because we don't want to overflow that. It's quite usual to overflow such a big h. If h is very big, we can overflow it. And then so if water is more than x, we can't do it there, so we shift R on the binary search up to the midpoint. And if water is less or equal to x, then we can do it there, and we shift L, so we try a little bit more in the binary search, and L is our answer. L is the valid answer at the end. So pretty straightforward, just binary search. I don't know why they're mixed here, but okay. So F I think I didn't see F that A can go up, A can be like 1, and we can have like all of them once, and 1 is of course divisible by 1, and thus making the problem quadratic in this case, where I time limit exceeded the first time. But you want to choose so some continuous subarray, and all of these hi needs to be divisible by hi plus 1, and the these fruits that we collect on this subarray cannot be more than k, so can be at most k. And for each starting point, I will know what can be at most the ending point. So what can be, because the divisibility here, if hi is divisible by hi plus 1, and hi plus 1 is divisible by hi plus 2, then this whole array can be like extended to some point when this divisibility breaks. So at this point, if I know what is the maximum point, then we can binary search what is the maximum number of fruits we can collect, and solving this problem in n log n time. So what I do is I first create some prefix array, then I create this. So DP, this is like dynamic programming last val. So like this is, if I'm standing at this position, what is my last position to the right such that I can extend this array H? So what is the last R that this from L to R will be constrained by, will actually satisfy this constraint? And if they're both, if I divide this I plus 1, then I can take the I plus 1's last valid position. So I can have the same position because I make this constraint possible. But if it's not, then the last valid is me itself. And now for each position that is L position, we want to binary search over R. So this is R starting at L and the last valid plus 1. Plus 1 is because this R here is not valid itself in the binary search, if you know what I mean. So then I binary search here. Then the sum is, I calculate the sum using prefix array because I want this to be really quickly. And then if the sum is smaller than k, I move I move R. If at the end, sometimes, if L is not equal to R, so R is not equal to L, this L is my R. So this L is equal to my smaller R, because this is from the binary search. So if these are some other positions, then I can just maximize the answer R minus L plus 1. But sometimes it happens so that this is just only equal to myself, so no element, like here, no element is valid. But we want to also check that the sum is smaller or equal to k, because sometimes, even though this element is valid in itself, but it could be larger than k, it's not guaranteed to be smaller. So the answer, if it's smaller, then the answer is maximized by 1. If not, it won't be maximized by 1, even though the array is actually with 1 length. So this is an edge case that you have to consider. That's problem F. And problem G. Problem G is just seeing that this invariant holds for, like, problem G is just seeing that for each operation you take away one A from the string. So you convert one A, and then this I explained it while I was solving it, but this kind of says, like, if I have a lot of A's and I have a B, then I will convert this to like a BC, and these are all A's here. Then I will do the same thing, but I will convert this AB into like this, and then so you see where I'm going with this. I can convert all of these A's with just this one B. I can shift them like this. And now the problem is, I have something like this. Can I convert all of the A's? I can convert all of the A's if there are two so for each B I can choose either to convert these A's, or if it was like this, I can choose either to convert the A's on the left of the B or the A's on the right of the B. And by a simple proof, we can say that, okay, if I have some A, B, A, B, A, B, A, B, for each B, I can choose, let's say, to choose to the right, right? So at the end, I will be left only one segment of A's won't be converted. And what I can further prove is that I can take the smallest segment of A's, even if it's inside, and budge them out. But if there are two consecutive B's anywhere, then I can choose that these B's are converted on the left and then these B's are converted all on the right, and thus making it. So essentially, you want to choose the smallest segment of A's between two B's. So sometimes it will be 0, or sometimes it will be 1, or sometimes it will be 2. But we want to choose the smallest and negate this. So essentially the solution is the following. We want to count all of the A's. Here we count all of the A's, and we choose the smallest segment such that this is possible, right? We negate the smallest segment. Sometimes the smallest segment can be 0 as well. That's the solution. I must, if I explain it, I must actually just explain it with this. So if I want to explain H, I will do it like this. Okay. In H you have some graph, but this graph there is one cycle in this graph, and there are some other branches. Why do we know this? Because this graph has n nodes, n vertices, and n edges. If you see something like this, you know that this is a tree with n-1 edges, so some tree, but there's one edge added on top of this, and this one edge creates a cycle. This one edge will create a cycle. So this is like a tree with one cycle. It's not a tree, it's a graph with one cycle. And we can present this, and so we want to say that there are two people, A and B. A wants to catch B. If they're both inside the cycle, if B is inside the cycle already, wherever A is, B can choose two ways, either left or right. So even A, if it's here, A wants to catch her, she will choose this or here or whatever. But let's say she will choose the other way around, right? So whatever one chooses, the other can negate it with something else. But the only thing where the case we need to worry about is when B, the prey that we want to catch, is outside the cycle. So let's say B is somewhere here, right? And now A, like let's say that this is B, and now A is very important where it will be. If B can arrive at the cycle and A is like somewhere far, can't arrive on time, then if B arrives at the cycle, we're left at the same conclusion that we can start B being here and then A being like closer here, and then just B will choose some place that A B will choose a counter strategy to A always and can always escape A. But let's assume that A is very close. then if the shortest distance from A to the point where B has a contact to the cycle is shorter than B, then A can come to here, and now B doesn't have anywhere to go, so B is cut out. So B has to go back, but A can catch her, and can always catch her. B cannot, like, just says that A will just close the door here, and it of course will catch her. B doesn't have another cycle to escape. So that's the idea. That's the idea in a nutshell. When it's in the cycle, it's of course can't catch her forever. But now the problem is, like, the shortest distance from A to the point where B's branch attached to the cycle, because B wants to come to the cycle as soon as possible and avoid A. This is the only way to avoid A. If B sticks out here, then A will go and will catch her. So there's no other way. And this is essentially the theory behind this problem, right? So yeah, so I will upload this video as soon as possible on YouTube, and hope you guys enjoyed this contest. This is Division 4 round. Check out the other videos on my channel as well, and I hope to see you in the next contest as well. Thank you guys so much for watching.